The second half of the session today, and we're going to actually next talk from Antonio Scriminski, and he's actually an intriguing title from Microsoft, going to decision forests and jungles for visual recognition. So, Antonio.
Thank you very much. Hello, everybody. I'll try to be relatively quick, go through what I want to tell you, and then leave plenty of time, hopefully, for questions, but I might not manage to do so, so we'll see how we get on. I'm based here in Cambridge, near the station. We have a team at Microsoft Research in Cambridge, and I'm part of Machine Learning and Perception. That's the name of the team, headed by Chris Bishop. So my interest is really not just in taking the latest, deep learning method, applying to my data, and great it works, but also understanding, what that method does and see whether we can improve on it. So one particular machine learning model that we've been working on for a number of years now is called decision forests, or random forests, better known as that. We didn't invent random forests; someone else did, 20 years ago or so. But I believe that we've been improving on them, and one variant of that is called jungles. I'll try to explain what that is. So, this is an overview. So I will give a semi-gentle introduction to machine learning. I know that at least half of you seem to be experts in machine learning, and so you will find this a little bit boring. But it's only a few slides, so bear with me. Hopefully, this will get all of us on the same page. Then I will describe forests and jungles in details, and then talk about at the end about some applications in semantic image segmentation. And there I will make some connections with deep neural networks, pros and cons of each technique. So let's get started. So in supervised machine learning, which is only one subset of the big family of machine learning tools, you have data represented as a multidimensional feature vector. You might have all those features available to you or not, and that's quite important. And in the supervised setting, you also have some labels attached to each data point. In this little drawing, I represent the feature vectors, multidimensional feature vectors, with this gray. Here's the pointer, with the gray. Okay, here we go. With the gray squares, and different colors represent different labels out of n, greater than 2. They could be class labels. So in here, I'm particularly focusing on perhaps the easiest of machine learning tasks, which is classification, just for illustration purposes. So what we want to do is, during the training phase, we push all this data, which is often very, very expensive to gather, especially in medical applications, push it through my favorite, training algorithm, and something comes out, which is some learned model, in this case, a classifier. It could be an SVM, it could be a decision tree, it could be a neural network where I've learned all the weights, and so on. So I just represented with this, iconic, graph. What we want to do, and this is important, is we want to ideally learn both the structure of the classifier, how many layers do we have in a neural network, how big are the layers, where do I apply, max pooling, where do I not, and also the parameters. And quite often we just look at optimizing the parameters, and some of these other variables are hand-defined. During the test phase, of course, we only have the data itself. We don't know what the label is, and that's precisely what we get by pushing the data through the existing classifier. So this is yellow, in this case, is the predicted class label. So the problem is that we have very high dimensional data. In this case, think of this as my images. I've got images of sharks and images of lizards. They get represented in a 2D feature space or in a 3D feature space. Again, this is just toy examples. And what I want to do is I want to be able to learn a generic function which separates not just the training data, of course, but also work well for future data which has not been seen before. And so this process is called induction. There is many other flavors of machine learning. There is transduction, there is semi-supervised learning, and many other things. And of course, the most important questions that we should ask ourselves here is, okay, what features am I going to use? Do I need to design them by hand, or do I want the training algorithm to learn those features automatically? What does automatically mean? I have to start from somewhere. So maybe what I want to do is I want to design by hand a family of all possible features. How do I define a family, and so on? So then what learning model? Do I use deep neural networks? Do you use forest? Do you use SVM? Do you use logistic regression? And once I have defined these, answer these questions, then what training algorithm? Is it going to be randomized? Is it going to be backpropagation? And so on. Of course, the biggest problem in machine learning of them all is overfitting. And so how do I make sure that whatever I have, is the right model? Not too big, not too small, so that I don't, I don't tend to fit to the noise in the data. So decision forests were invented as a next step up from decision trees, which have been with us for donkey's years really, as a way of improving the generalization, and therefore reducing the overfitting that was inherent and quite visible when using decision trees. So let me explain a little bit more about decision trees and decision forests. So a decision tree is nothing else but a data structure. Of course, it is made of a root node. You have got some internal nodes, and you have got some leaf nodes. The internal nodes, in this case, we call them also split nodes. The reason for this name is because some decisions are made in the internal split nodes. For instance, this is a picture of my kids, and if I want to classify this image as belonging to outdoors or indoors scenes, then I might think of doing this manually in a rule-based system, and say, oh, clearly if the sky is there, it's going to be an outdoor scene. How do I detect the sky? I can ask the question, is the top part of this picture blue? And then if it is blue, then I do something else. I can check whether the bottom half of the picture is also blue, in which case, if it is also blue, then maybe I'm staring at a blue wall, and it might be an indoor scene. So you can see that a decision tree can represent this hierarchical structure of questions that I can ask to probe different features within the data that I've got as input, in this case an image. And 40 years ago, or even more, people used to use this sort of rule-based systems all the time, manually designed, hierarchical structured rule-based systems. Of course, in machine learning, well, in computer vision, we know that this will never work, and it doesn't, unfortunately, because every time you come up with an idea with the next question probe to ask, there are a million exceptions, and then you start writing another million if statements to try to deal with those exceptions. So the key here is that in a decision, we can still use a decision tree to structure the sequence of questions to ask, but now we use machine learning automatic training algorithms to figure out both what the structure of this tree should look like and what questions to ask. Okay, so that's the difference. So a decision tree or a decision forest is nothing but what people used to do 40 years ago, with a big important difference that now all these rules are learned from data, from tons and tons of training data. So here is how the training algorithm works for a toy example. Imagine that we've got two features, x1 and x2, and we've got a bunch of training points represented by these different circles, and they belong to 4 different classes, color-coded. So what you can do is you can say, oh, okay, I start at the root, and I need to learn what question to ask, how to probe the data, to try to separate it into as pure classes, as pure predictions as possible. And so I can start with a randomly drawn hyperplane, this black dotted line, going through my data space, and I say, oh, does this separation work well? Do I get reasonably pure separation of the 4 different colors, left and right, or top or bottom, or not? Or does this other one work better? Does this one work better? And so on. I can randomly try many different such options until for a limited period of time, depending on what my computational budget is, And then I say, out of all the things I've tried, this is the hyperplane that works best. And you can measure this. You measure this using information gain, for instance, based on Shannon entropy or whatever else you like Gini index. And now, the important thing is that you recurse. You carry on doing this operation, but only on half plane, half space. And so, conditioned on the fact that at the root node, we have selected this feature, this hyperplane, to be my split function. Now let's look at the left subplane, and I choose this hyperplane now, and then to the right, and so on. And at some point I stop. So each of these 4 quadrants here represents a leaf in this very small tree, which says that if I reach this leaf, then I can predict my class to be purple, red, green, blue. I might still have some mixed values here, and that's fine. We'll see that especially the idea of having multiple trees takes care of these issues. So this is the objective function that I try to reduce each iteration when I train maximize in this case at each node. It's just a standard definition of information gain for multi-class problems. But what we did was pushing these ideas a little bit further, and this is just one small step in which we did this. So most people, when using these sort of techniques, they use what's called axis-aligned features, which means that if I'm talking about pixels, maybe I just look at one color channel at a time, or one feature at a time. It could be the response of a bank of filters. I just look at one of them at a time. This corresponds to having hyperplanes which are aligned with the major axis, but the data might not be structured in that way, and so oriented hyperplanes might work best. And so sometimes this is called oblique trees, but also you can have many more different families of hypersurfaces to separate your data into one or another set. In the case of 2D, you could use conic sections and so on. So we have done. Okay. So then, once the training has been done, effectively we have learned a tree structure. The tree doesn't necessarily need to be balanced, and it looks a little bit like this. Here they are very difficult to see on purpose edges, because they represent that there is very high entropy here. There isn't very much information content. As you go down the tree, the entropy increases and increases, and so you see that different colors become more distinct, because you have more information when more certainty when you go towards the leaves of the tree. And so now at test time, given my test input data, which might be an image, for instance, I ask the first question. I take the left or right branch depending on what the answer of that test is, and then I get to this split point. I get this route, and so on. I follow the route until I reach a certain leaf. At that leaf, I've got a probability distribution over the n classes that we're interested in. And so what I could do is I could simply say, okay, I look at this probability distribution. This is a completely empirical histogram, for instance. And then I say the class attached to my test input is the green class, whatever that represents. It turned out that if rather than having a single tree and training it to death until we have absolutely pure leaf nodes, we instead stop a little bit earlier and train an ensemble of many trees. In this case, we have 4 trees, where we have added some randomness during the training process. Then everything works better. And this is a bit counterintuitive, but it has been demonstrated over and over again. So that's a decision for it. It's a set of randomly trained decision trees. So you can choose different ways in which to aggregate the responses over the different trees. So for instance, if our problem is that of regression rather than classification, so the y is a continuous variable that we want to estimate, then at each leaf we can store Gaussian-like probability density functions And so if the same input data point is tested through all 4 trees, it will reach 4 different leaves. It will reach, therefore, 4 different distributions. Now, what you can do to aggregate all of these and come up with a single answer is, for instance, very simply, take the sum, the average, of all these, the mean of all these. And what you will see is that, the trees which are more highly confident, like the red one, will dominate. And so, the ones like the green or blue, which are associated with very high spread, very high uncertainty, then will tend to be ignored, through this, mean operation. And of course, this is not the only way in which you can do this. Now, my colleague Jamie Shotton and myself applied these sort of techniques, to a very wide range of data, not just computer vision data, but also high multidimensional and multimodality, data from the medical imaging analysis space, and try to understand the behavior of decision trees and decision forests. For instance, what happens, if you increase the depth of the tree? So what happens is that, for instance, you get more certainty, in this little plot. This is my attempt at showing classification results on a 2D space, where I have this spiral arm representing 4 different classes. Sorry, just a sec. And also, what happens if, in the other axis, I change the type of split function. Rather than having axis-aligned features or split functions, what happens if I have oriented, hyperplanes at any orientation, or more complex, higher degree of freedom models? So you see, for instance, that going from this picture to this, the level of smoothness of the prediction increases dramatically, and this is an indication that there is a lot of artifacts and overfitting going on here, and this might work better. But of course, there is also the opposite problem, that if you increase the number of model parameters too much, then you're going to have issues there too when you fit to noise. So this is decision forest. So do they solve everything? Well, they work pretty well in practice, and this is, for instance, what is used, when you play Xbox games with your Kinect. The Kinect software is based entirely on these sort of things. However, there are some issues. For instance, these trees, for real problems in computer vision, might grow to be really, really big. So, for instance, in Kinect, we use a forest of only 3 trees with 20 level trees. And so, that is a lot of nodes. So it takes up a lot of memory in your Xbox machine. But also the bigger problem is that training them is difficult, because you need to have enough data for it to reach each of these 2 to the 20 leaves, which is a lot of data. So what if we take some nodes and merge them together? Then we get a DAG, a directly acyclical graph. Like these red nodes have been merged together, and we can do this. For instance, it looks like I won't have time to go through all the details of how this is done, but you can imagine that if you grow a decision tree, and then at some intermediate level, you find 2 nodes, say at the same level, depth 10 or 11 or whatever it is, and those 2 nodes clearly belong to different branches of the tree because there are no cycles. But they express the same training statistics, like say the maximum, the highest class in the histogram is the same. And then you can say, oh, maybe there is no point in keeping these 2 nodes as separate ones, separate path. I might as well merge them. By doing this, you reduce the number of parameters in your model, and therefore you reduce the chances of overfitting. And so that's what we show, with a very quick toy example. Imagine that we have images of cows and sheep as well, and we want to be able to, given a patch, recognize whether it belongs to grass or animal. And the grass may look very green or very yellow, like in my own garden. And what you can do is well, again, I'm not although this patch and this patch belong to very different areas in the data space, in the feature representation, I might want to say that this whole blob here is belongs to the same leaf in my graph representation. And so I'm going to skip through all of this step-by-step explanation to just show that the DAG would partition this feature space into one big leaf here that, despite the fact that there is no training data in the middle, manages to say that all of this belongs to the class grass, and therefore this is an intuitive explanation of how DAGs can help increase the generalization power better than trees. And so for this example, a DAG will look like this. So here I've got sheep patches, here I've got cow patches, and here I've got grass with different levels of illumination and brightness. So applications. So we applied both decision forests and decision jungles for problems of semantic image segmentation nature. Image segmentation, of course, a lot of us have been trying to do this for many years, but it is still with us. It is still around because we can get it better and better and better, faster and faster and faster. Also, when we talk about semantic image segmentation, this is different from doing unsupervised image segmentation first and then classifying the regions as belonging to certain objects. Here what we want to do is we want to do the two things at once, because we believe that by doing them at once jointly we can get better results. Some issues that we need to always consider are to do with the level of spatial smoothness, or being able to reconstruct long thin structures, but also semantic context. So in medical images, for instance, it is clear that we want to explore and exploit the use of semantic context. The heart is defined as the heart, not just because it looks like the heart, but also because it sits in between the lungs. And so that information is clearly very important. So, we cast the problem of semantic image segmentation as that of, given a pixel in an image, we assign a class value to that pixel. Again, we don't do segmentation first and recognition second. We recognize the class that each individual pixel belongs to straight away. And so we can do this, for instance, for this image, using random forest, pixel-wise, classification. And as you would expect, we do get some results, but they are very noisy. And for instance, if what we want is only to segment the face and not the hand, in this case, we have a clear problem. So what we can do is we can, this sort of techniques, decision forests have also been used, like I said, in Kinect, because when you play a game, we want to be able to extract the skeleton of the player from a depth image. This is the input. But before we can do that, in order to do that reliably, we first analyze each individual pixel of this depth image and assign a class label to it. Each pixel is said to belong to one of 32 or 31 body parts. So left hand, right hand, left part of my head, right part of my head. So this is what happens, under the hood when you play Kinect games, and this is done on your Xbox in much higher than real time. This is using as little as possible of the hardware resources. So decision forests are interesting not just because they are good in terms of accuracy, but also because the high level of parallelization and the conditional computation that happens that makes them very efficient. So we have used decision jungles since Kinect has come out, and what you can see is that just by switching from decision forest to decision jungles, visually the results do not look incredibly different, but there are some differences in the sense that this is much smoother, less pixel-wise noise, same here, without having to impose any mark random field or any other smoothness priors, and with lower parametric models. So there is a number of advantages there. So also numerically, quantitatively, we can see that these orange curves behave much better than the green and blue counterparts, which are based on decision trees for the same number, the same total number of nodes. Therefore, for the same complexity of algorithm or memory requirements. Now, I wanted to talk about, okay, very briefly. So, like I said, in Kinect, we can train up to 20 levels deep trees. Not because we wouldn't be better if we had 21 or 22. The accuracy keeps improving and increasing, but we just can't. It's too many nodes. It's too much training time, and also test time. We don't have enough computational budget. But with DAGs, with decision DAGs, we can train up to 60 levels. Okay, because the memory footprint is so much smaller, and the deeper we go, the more accuracy we get. So this is a 60-level structure, yet it is not deep. Okay, this is important. It is not deep in the sense of deep learning. So let me quickly conclude with some consideration on deep learning. What is deep learning? Deep learning means having a chain of transformations of the data that is learned. So in particular, in neural networks, there are many flavors of deep learning. For instance, the two most famous are deep RBMs, restricted Boltzmann machines, which are generative models, and then deep neural networks, or also the convolutional flavor of neural networks. These are discriminative models. So if we have a deep neural network, like in this case, we have inputs and then hidden layers and output units. The important thing that makes this model deep is the fact that the nonlinear transformations between each level, each layer, I should say, are learned during the training process. This does not happen in decision trees, and it does not happen in decision DAGs, because in those, the data is just copied from one node to the other. There is no transformation applied to it. So, despite the fact that for ImageNet, for instance, the DNNs used there are only around 20 levels deep, the biggest ones. These are deep levels, and the previous ones, which were 60 levels, are not deep. Now, I would like to talk to you more about the connection between jungles and deep models, and how to turn jungles into deep models through a technique called entanglement. But I've run out of time, and I would like to take at least a couple of questions from you. So that's it.
Thank you very much. As before, we're going to leave questions, and I've actually already got some written down for afterwards. So
okay.
We'll call you back up at the end of the session.
Okay, that's fine.
Our next speaker.
This is the most important slide of them all, though. Read it carefully.
But I think really, thank you very much.
Thank you.
Really, actually interesting presentation. Our next speaker is Andrew Wallace.